So welcome back to EE210B. Okay, this is lecture number 7, and we will be talking today about Lipschitz conditions. Okay, so this is still part of the background material that I would like you to be familiar with, because we'll be using this material extensively in the course. Okay, so that at least you know where to refer to when you need to know more about it. Okay. Now, if you remember last time, I talked about mean value theorems, right? That was Appendix D in the text. The material for today is based on Appendix E. Okay, so what we did last time, I started with a function. I started with a function g of z, real valued function. It wasn't necessarily convex. I just required it to be differentiable. Okay, and I derived relations that provided you with expressions for the increments in the function and increments in the gradients of the function. Remember, these were similar to a Taylor series expansion, where on the right-hand side you have an expression that tells you exactly what the expansion is, rather than terms that you would usually ignore, right? So if you remember, the mean value theorems led to relations like this. Okay, so G is a function which is not necessarily convex, and I would like to expand it around Z0, right? So I have a small perturbation around Z0, and what this expression tells me, it tells me that G at that point, I can express it in terms of G at Z0 in this form, right? The left-hand side is equal to the right-hand side plus a term here, right? So that's what the mean value theorem allows you to do, and that term depends on the integral of the gradient vector of the function, right? And this is an integral over a scalar parameter, and delta z is by how the size of the step. Remember, we did this last time? So this was for the function, and the relation below it is for the gradient vector itself, right? So we have one relation for the gradient vector, and therefore here you will have the Hessian, and the first relation is for the function itself. Now, remember, the gradient relative to z, which is a column, by definition is a row vector, right? That's why you have delta z appearing on the left, so that the dimensions match. And remember again that the Hessian matrix, in the real case, when z is real, is m by m. And then we had the complex version of this when z was complex, right? The first relation was the same. The second relation was very similar, except that I had to extend these gradient vectors. I had to define a block vector containing the gradient relative to z, the gradient relative to z star, here and there. And the Hessian matrix in that case was 2m by 2m, right? And this was also extended, right? So this is what we did last time. These are useful relations, mean value theorem relations. They tell you how to expand a function or its gradient around a particular point, and they tell you exactly what the difference is, right? So what I'm going to do now, I'm going to take this a step further. What if my function is convex? Can I say more? Okay, so I'm going to work these relations a little bit more, extract more information from them, because the cost functions that we'll be minimizing in this course, they will be convex. So for these cost functions, there is more I can say from these relations. For example, if the function g of z is convex, let's say strongly convex, it will have a unique minimum, right? If it has a unique minimum and that minimum is z0, the gradient at z0 will be 0, right? Very good. Okay? So I can replace this expression for the gradient up here, right? The second equation gives me an expression for the gradient. I can replace it inside the first integral. I will end up with an expression that tells me what the increment will be in terms of the Hessian now, right? I can use that. I will be using that very soon. And by following this argument, okay, we'll be able to bound, we'll be able to do two things. We'll be able to say how big this increment can be. We'll be able to bound it from below and from above. Not just give an expression to it, but we'll be able to say the norm of this increment lies between these two bounds, number one. and we will be able to assess the size of this term. Okay? So these are additional pieces of information that I would like to derive for convex functions, okay, starting from these relations. Okay, so today's lecture is an application of these relations to the particular case when I have a convex function, for both cases when z is real and complex. Fine? So let's start, okay? So let's start with the case when z is real, okay? And g is convex. So in that case, I'm going to take this z0 to be the minimum, okay? In that case, the gradient evaluated at z0 plus delta z, you come here, if I replace this delta z by t delta z, this delta z here will be replaced by t times delta z, and this delta z here will be replaced by t times delta z, right? So if you do that, you get exactly this relation, right? I haven't done anything, okay, anything strange so far. All I did, I started with a function g of z, and I assumed that I picked z sub 0 to be z sub 0, the minimum, right? Remember my notation when I put the O on top, that argument refers to the minimum of the function, right? So if I pick my z sub 0 to be the minimum, right, then the two relations I gave you before combined give you this result, right? So far so good, right? This is for a general function g of z evaluated at the minimum or expanded around the minimum, okay. So now, very often in this course, and I will be talking more about this later, okay, we'll be dealing with cost functions whose Hessian matrices will be bounded. Okay, now if you remember when I defined strongly convex functions, if g of z is nu strongly convex, I showed in a previous lecture, right, that this is equivalent to saying that the Hessian of that function is lower bounded by nu I. Remember that? That was an equivalent condition for strong convexity, right? The Hessian matrix of the function, no matter what z is, will always be lower bounded from below by nu I. Let's assume that it is upper bounded as well from above. Okay, we'll encounter many situations in this course where the cost functions that we are interested in satisfy a condition like this. So now I have a cost function whose Hessian matrix is bounded from below and from above. The lower limit, I'm calling it nu. The upper limit, I'm calling it delta I, right? You understand what this notation is. This is a matrix less than or equal to another matrix. This means if you subtract, if I call this matrix capital A minus capital B, the difference is non-negative, non-positive definite, right? That's what the less than or equal to 0 there says, right? All the eigenvalues are less than or equal to 0, okay? So if you come back to this relation, which is general for any function with second order derivatives, right? If you come back to this function, you see I'm telling you that the Hessian is bounded by delta. So if I compute the norm, right, of both sides, this delta, the norm of the Hessian is bounded by delta, right? So that becomes a constant. You take it out of the integral. You have a double integral with a t, right? You integrate twice, right? You integrate over t squared over 2. You integrate over r. So you end up with t squared over 2 between 0 and 1. That's 1/2, right? Okay. So because of that, you end up getting, and remember, you have a delta z here and a delta z there, right? This is an inner product becomes the norm of delta z squared. Okay, so this is very immediate to get, that because the Hessian matrix is bounded from above, okay, because the Hessian matrix is bounded from above, we are going to get this statement here, okay, we are going to get this statement here, right? If you go back, by the way, if I go back here, even though I wrote norm, you see I don't need that. Okay, I don't need that. I don't need to take the norm. Why? Because this Hessian matrix is non-negative definite, right? So the quantity on the right-hand side is always non-negative, okay? It's always non-negative, right? If you remember that, if I have a matrix A, this is a matrix A, we'll be talking in the next lecture about some basic matrix results, and this is hopefully one that you know. If I have a matrix A which is symmetric and non-negative definite, its eigenvalues are between lambda min and lambda max, right? Then you know that X transpose AX will be between lambda max, norm of A squared, and lambda min, norm of A squared, right? Okay, this is related to something called the Rayleigh-Ritz characterization of eigenvalues. We'll be talking about it in the next lecture, but I believe you may have seen it. Okay, so this is what's happening here. You see, I have a vector and its transpose, and I have a non-negative definite matrix here in the middle. Okay, so this quantity here will be upper bounded by delta, the norm of delta z squared, and there is the 1/2, and lower bounded by what's lambda min in this case? Because the Hessian matrix, my Hessian matrix, in this case, is upper bounded by delta, by assumption, and lower bounded by nu, right? Okay? So this nu is definitely smaller than the lambda min of the matrix, and this delta is larger than the lambda max of the matrix, right? Okay? Yes. No, sorry. No, yes. Norm, this is norm of x. Sorry, norm of x. Okay, norm of x. Okay, and here also, I didn't need to write norms, right? Just to keep it clear. Okay. So it's not difficult for you to conclude that this result holds, right? Okay. So all I have shown so far is that if I have a strongly convex function g of z, and therefore its Hessian matrix is bounded from below because of strong convexity, I'm assuming in addition that's bounded by above, from above by delta. Okay, if this happens, if the Hessian is between two bounds, then the increments will be between two bounds, right? Fine, between two bounds. That's what we have shown so far. A similar result will hold when z is complex as well. I'll mention that briefly later. Now, why is this result useful? So this is the first conclusion. Okay, so why is this result useful? And remember, this z0 here is the minimum, right? Z0 is the minimum of the function, okay? So one implication, I used to have g of z minus g of z0. So I moved g of z0 to the other side of the inequality, right? So one implication is that every strongly convex function can be sandwiched between two quadratics, right? You see, this is a quadratic as a function of z, quadratic in z. And this is another quadratic in z, right? So every strongly convex function, you can bound it, right? From below by a quadratic function of z, and from above by a quadratic function of z, right? If you have some strongly quadratic function here, you can find a quadratic from below and a quadratic from above that always bounded. That's one conclusion, useful conclusion, okay? Sorry? Oh yes, sorry, this is just, I did not draw it with precision. I'm just trying to convey the idea, right? Okay, because when z is equal to z0, right, they both have the same value. So at the optimum, they touch, okay? Right, so if you want to be precise, if this is the minimum, right, so you will have a quadratic from below and a quadratic from above. This is more difficult to draw, but that you get the idea, okay? That's what this result is trying to say, okay? So far, so good, okay? Now, let's take this a step further. There is another conclusion I can get from this result, which will be very useful for us later, okay? And this second conclusion will hold if I introduce an additional assumption. So far, I assume that the Hessian is bounded from above, right? Bounded from above. Besides the strong convexity, that's a given. If the Hessian is bounded from above, you get the conclusion I showed you before, that the function g of z can be sandwiched between two quadratics. Fine. Number two, let's assume in addition, okay, that the Hessian matrix is Lipschitz. Okay, so what does that mean? I sometimes refer to this by saying that the Hessian matrix is smooth enough at the minimum. Okay, what does that mean? It means if you are at the minimum and you perturb it a little bit, the change in the Hessian matrix, right, is bounded. Okay, is bounded by the size of the step that you took. Okay, that's what I mean by saying that the Hessian matrix is smooth, and this is what it means to say that the Hessian matrix function is Lipschitz. Okay, that's what Lipschitz means. Okay, if you have a function, in general, if you have a function f, and you want to say that it is Lipschitz, this is essentially what we say. Okay, that there is some constant. Here I called it kappa, let's say x, L. That this holds for some constant L, okay, for all x and delta x up there, okay? That's the definition of what a Lipschitz function means. Here I'm saying that I want the Hessian matrix of the function to be Lipschitz. What this means is that the function is well behaved such that if I move a little bit away from the minimum, the Hessian changes only in proportion to this step. Okay, very good. Now,
which norm of the matrix?
Sorry, here I'm using the Euclidean norm. Okay, so I'm using the two-induced norm. All the definitions I will be using are relative to the two-induced norm. What is the two-induced norm of a matrix? Again, in my review of basic matrix results, you will know what it is, but I assume that you have heard that before. The maximum singular value of a matrix, right? That's a norm. So when I write the norm, the two norm of a vector, you all understand what it is. The two norm of a vector induces a two norm on the matrix, which is the maximum singular value of the matrix. So what this means, the maximum singular value is upper bounded by some constant times the two norm, right? Okay. Now, I'm saying here that I would like the Hessian matrix to be locally Lipschitz, okay, locally Lipschitz. What that means, okay, or Lipschitz continuous if you want to be more precise, okay, but I will not be pronouncing all these words all the time, right? So, locally means I would like this property to hold close enough to Z0. That's good enough for us, okay? Later I'm going to show you actually that if you require this condition to hold, locally, it will turn out to hold globally as well. That for any z and delta z, for any delta z, this will hold. For a different kappa. I will show this later, okay? Let's not worry about that for now, okay? So let's assume for now that my cost function satisfies this. For example, if g of z were a quadratic function, does it satisfy this condition, yes or no? Because the Hessian of a quadratic function is independent of z, right? So that you will get always 0 on the left. So a quadratic function automatically satisfies this. But there are, of course, other functions that satisfy this. Some of them you will do in your homework problem, okay? Okay. So if this is the case, what is the second conclusion I can get from this, okay? To say that the Hessian is Lipschitz, I mean locally Lipschitz continuous, okay? To say that it is Lipschitz, essentially you are saying that this quantity on the left is equal to the second quantity, this is the last equation on the slide, plus some small perturbation, but the size of that perturbation is not bigger than the norm of delta z. What this notation, big O, means is that this quantity here, right, is upper bounded by some constant times this norm. Okay? So that's what this means that the difference is of the order of the norm of delta z. The difference is something that is some constant times the norm of delta z, upper bounded by some constant times the norm of delta z. Okay, that's what this means. Okay, so do you see how this follows from this? Okay, okay. Now, if this is the case, remember what I showed in the previous lemma? Okay, what did I show here? I showed that the increment involves an integral of the Hessian, right? But right now I showed you, if the Hessian is smooth enough, the Haitian at this small update around Z0, I can relate it to the Haitian at Z0 itself plus a small error, right? Okay. Now, if I put the Haitian of Z0 here, you see? So let's clean this so that you can see where I'm going with this. Okay. So here you will get the Haitian at Z0 plus an error which is of the size of delta Z, right? So when you compute this integral, you will get two terms. Okay, what will you get? You will get delta Z transpose times the Haitian at Z0 times delta Z, right? Plus norm of delta Z squared coming from this inner product that times something of the order of delta Z, correct? Correct? So the conclusion is, look here, this is a weighted norm, right? This is a vector times a non-negative definite matrix. Actually, in this particular case, it is positive definite because the function is strongly convex, right? So this is a weighted norm, right? There is 1/2 that I forgot that comes from this T. Okay, there is 1/2 in front of this, correct? So the conclusion from this is that the increment is equal to a weighted norm of delta Z weighted by 1/2 the Haitian at Z0, right? Plus an error term which depends on the cubic power of the norm of Z, delta Z. Correct? Because this is a squared, this is, right? This is a cubic power of norm of delta Z. So the second conclusion that I wanted to say is, that follows from the first lemma, is actually I can find an expression for this difference. I can tell you exactly what the value, not exactly, I can approximate well what the value of the right-hand side is. This is it. It is a weighted norm of delta Z. I wrote the delta the other way around, but I know you understand. Right? This is delta, not, okay? So delta Z squared, this is a weighted norm, right? With the Haitian. So you find the Haitian at Z0, okay? This norm, this quantity here is by how much G is going to change. And the size, and this is a good approximation for that because the size of the error will depend on the cubic power of delta Z. If you take a very small step, the cubic power of that will be much smaller, right? So this is a good approximation to this degree. You understand? So this is the second conclusion that I wanted to mention to you. Okay, so if I put these things together, okay, so this is what the calculation I did on that slide. And this notation stands for this, right? Okay. So this is the conclusion. Okay, this is the second conclusion, right? So you see, for convex functions, I was able to say, to extract these two pieces of information from the mean value theorem, okay? That this increment is bounded between two bounds. I know how the smallest it can be, and I know the largest it can be, number one. And not only that, I can find a good expression for it. I can tell you, and I can tell you the size of the error as well. And this is a good approximation for it up to this amount of error, right? And the important thing to note here is that no matter what your strongly convex function is, okay, no matter how it looks like, the change in the function is a squared Euclidean norm, a weighted Euclidean norm, okay? And this is very useful. Because what this says is later when we want to assess the performance of algorithms that are performing adaptation or learning or estimation over networks, okay, very often you would like to know when you are updating an algorithm, what are you doing when you are updating an algorithm? You are moving from one estimate for the minimizer to another estimate to another estimate to another estimate. You are moving from one estimate to another location, right? And you would like to know, to assess by how much this algorithm is improving, for example, at every step, right? So what this result is telling you is that a good way for you to assess that is to simply compute a quadratic function of the step, right? A quadratic function of the step. The nonlinearity of the function itself doesn't come here, right? It only enters through the Hessian matrix, okay? Fine. So we will be using this result in that way when we do analysis later in this course, okay? Very good. Fine. This is an example. A quadratic function, g of z is quadratic, okay? So it's convex. If C is symmetric and positive definite, it's convex, right? The Hessian matrix is 2C, okay. The Hessian matrix is 2C, right? So it's bounded between 2 lambda max of C and 2 lambda min of C, right? So nu is 2 lambda min, delta is 2 lambda max, right? Okay. So if you find what the value of this function is at its minimum, okay, and you can bound it between delta over 2 delta z squared, right, and g at z0 nu over 2 delta of z squared, right? That's what we showed before. This delta is lambda max of 2c, right? Which is 2 lambda max of c. So delta over 2 here will be replaced by lambda max of c. And similarly, nu over 2 will be replaced by lambda min of c. Right? That's the calculations in this example. You understand where we are going? Okay, I'll come back to this expression, but I just want to show you. You see, this is delta, this is nu. Therefore, the Hessian is between these two limits. If you apply directly the results of the theorem I showed you, okay, the value of the function at the minimum, you can find the minimum. How do you find the minimum? Compute the gradient, set it equal to 0, right? This is the gradient. Set it equal to 0, you find the minimum. Evaluate the function at the minimum, here it is. And then from the lemma, the function will be bounded by this and will be bounded by that, right? Now, of course, in the quadratic case, you don't need to go through these lemmas. These calculations, you can do them directly, right? You can do them directly because you know the function. It has a very simple form. And for the quadratic function, by the way, for the quadratic function, this is a completion of squares argument. You can always write it as the minimum value plus a quadratic term that involves the difference between z and the optimum value of g of z, right? For any quadratic function. If you have any quadratic function like this, you can always express it as, this is just algebra, you can verify that this is the case, z minus z0 transpose c z minus z0, right? This is just some algebra. You know what g of z0 is. It is this first term, right? So if you expand this, you get that. So you can see right away that g is g of 0 plus the maximum this can be. The maximum this can be is lambda max, right, of c times the norm of z minus z0 squared, okay? So you don't need dilemmas in this case, but I'm just showing it as an illustration, okay? That's one. Okay, and then the second component of the lemma is that I have an expression for the increment, right? What did the expression say? It will be it will be the squared norm of the step times here, weighted relative to the 1/2 of the Hessian. The Hessian was 2c, so it becomes c. Now, the lemma said that this is approximate, but for the quadratic case, this is actually exact, right? Because for the quadratic case, g minus g of 0, right? You can see this is the norm of z minus z0 relative to c with weight c. It's exact, okay? Anyway, so this example illustrates, right? Okay, so for quadratics, for a quadratic function, this is exact, okay? But the lemma is more general than that, okay? For example, you can apply the lemma to the logistic function. You will prove in one of your homework problems that the logistic function, the regularized logistic function, is strongly convex, right? So you can derive and apply relations like this to the logistic function, okay? And other functions as well, okay? Fine? Okay. So that's that all I did, I started from the mean value theorem, and I showed you that I can say more if my function is convex, right? I can bound the increment between two bounds, and I can give you an expression to the increment which is accurate to the order of delta z cubed, right? That's what we did. And similar relations will hold when z is complex. That's the later part of this lecture. Okay, so I'll go through that a little bit more quickly because it's very similar. But before I get there, I want to provide an interpretation of what does it mean for the Hessian matrix to be smooth. Remember, how did I define it to be smooth? I said the Hessian is Lipschitz, right? That's what I mean by saying the function of the Hessian matrix is smooth at the minimum. Okay? I said that, sorry, in this part I'm actually going to show you two things. One is I'm going to revisit the smoothness condition on the Hessian, okay, and show you that that local smoothness condition is actually leads to a global smoothness condition. That's one thing. The second thing I want to show you is this result. Okay, is this result. I assume that the Hessian is upper bounded by delta I, right? That was a condition I needed to be able to arrive at the conclusions I got. I want to show here that saying that the Hessian is upper bounded by delta is equivalent to saying that the gradient vector is Lipschitz with delta. Is delta Lipschitz. That's the language we use. Is delta Lipschitz. Okay? So you will hear Lipschitz a lot in this course, okay? But it's nothing more than saying, when I say the gradient is Lipschitz or a function is Lipschitz, it just means that the increments in the function are upper bounded by some constant, the increments in the argument. That's all. Okay? Fine? Now, so I want to show that this implies this and this implies that. By the way, intuitively, it's not difficult for you to see the connection. How do you define the derivative of a function? Let's say in the scalar case, f of x plus delta x minus f of x over delta x, right? That's the derivative. You see, if you take this norm and you divide it by that norm, right? It is, and then take the limit as z goes to the other z. It's almost like computing, right, the norm of a second order derivative, right? So it's not difficult for you intuitively to see that these two things should be related. The proof will make this argument precise, right? Okay. Now, so can you see an advantage why it may be advantageous to state that condition in this form and not in the first form? Because sometimes the function may not be second order differentiable. It may just be first order differentiable. So sometimes it's more convenient to state the condition just at this level rather than go all the way to that level. You understand? So that's why I would like to show that these two things are equivalent, so that if you see it stated only as equation 21, you'll understand that this is actually related to the other condition that we are using, right? Okay. So this is the next lemma. Okay. Saying that the Hessian is upper bounded by delta is equivalent to saying that the gradient vector itself is Lipschitz by the same amount delta. Okay, fine? And then we'll have a similar result in the complex case as well. I'm just, okay, stating these facts. So let's prove this. So this is an if and only if statement, right? To prove it, you have to prove it in both ways, right? If the Hessian is bounded, then the Lipschitz condition holds. If the Lipschitz condition holds, then the Hessian is bounded, right? You have the proof in the notes. I can mention it quickly here. Okay, so let's assume that the Hessian is bounded, okay? We know that it's actually bounded from below as well. At least by 0, it's bounded from below, okay? Now, consider this function h, which is the gradient of g. Okay, h is the gradient of g, right? So this is a vector, because the gradient relative to a row is a column vector. So h is a column vector, okay? And apply the mean value theorem to this column vector. Nothing so far, right? Just apply the mean. The difference is the integral of the gradient of h. Well, the gradient of h will be the Hessian of g, right? Okay. So here I just wrote down the mean value theorem. This will now be the Hessian of g, right? Okay. So If this is the Hessian of G, and the Hessian of G is bounded by delta, also by 0. For strongly convex, actually, it's bounded by nu. But this result holds even for just purely convex functions, okay? Then, if you take the norm now, right? So this norm here will be upper bounded by delta times the norm of z, right? The norm of the difference of the z's. That's exactly the Lipschitz condition, right? So if the Hessian is bounded, then it's obvious to show that the norm of the difference of two gradients is bounded by delta times the norm of the difference of z's. So one direction is obvious. Let's prove the other direction. Okay? Here it is, okay? So let's prove the other direction. So now I'm assuming that the function has Lipschitz gradient, and I want to show that the Hessian is bounded, right? The opposite. Okay? So let's introduce this function, which is the gradient evaluated at z plus t delta z. So f of t is a function of a scalar variable, right? We did this last time. So if I differentiate it relative to t, you differentiate the argument here, the inside relative to t, you get delta z. And then you differentiate the function itself, you differentiate the function itself relative to z, you get the Hessian, right? Fine so far? Okay. So f of t is just a function of a scalar variable. So the derivatives of that function is your usual notion of derivatives, right, from calculus 1, right? So if I evaluate the function at two different points, t plus delta t, okay? So this is the value of the function at t, okay? And sorry, is there something missing? Oh no, okay, I'm just writing down the definition of the function, right? So this is f of t, right? And this is f of t plus delta t, okay? But the function, by assumption, is Lipschitz. The gradient is Lipschitz, right? So this is the gradient at one point, this is the gradient at a displaced point. So this will be upper bounded by delta times the size of the displacement. The size of the displacement is what? Delta t, delta z. That's the difference, right? Okay. So if the gradient is Lipschitz, I know so far that this is upper bounded by that. Divide by delta t. So you get that the ratio is upper bounded by that. And take the limit as delta t goes to 0. Okay? So this will be, right, the norm, right? The norm of that derivative, right? F is a function of a scalar, but f itself is a vector, right? Okay? Very good. So far, this is what I have, okay? This is what I have. If you go back, okay? Remember, the derivative of the function is the Hessian times delta z. So I'm going to replace this norm by the Hessian times delta z, right? This is what I have shown so far. I have shown that the Hessian times delta z, the norm of that is upper bounded by delta times delta z, right? So I have shown that a matrix times some x, think about it like this, is upper bounded by delta the norm of x, right? Let's just write a and x to make the notation simple. I want to conclude from this that this implies that this a, which is non-negative, is actually upper bounded by delta, right? This is what I want to conclude from this. Okay, very good. So if you continue, I'm going to square both sides, okay? You see, I had the norm of ax squared would be less than or equal to delta squared, the norm of x squared, right? Fine? Okay. Now, what is here the norm of ax squared? This is x transpose A. Remember, A is symmetric because it's a Hessian matrix. Times ax, so this becomes a squared x, is less than or equal to delta squared x transpose x, right? So this tells you that x transpose a squared minus delta squared I x is less than or equal to 0 for any x. So this tells you that this matrix here this relation is true for every, right? It's true. So the A squared, and remember, A is symmetric and non-negative, positive definite or non-negative definite, right? So from this you can conclude that A is upper bounded by delta, right? Okay. So we proved that lemma. Okay, here it is. We proved this lemma. Okay. So if you go back, you see, so this lemma only requires G to be convex, not necessarily strongly convex. Fine. So whenever I say the Hessian is upper bounded or the gradient is Lipschitz, now you know that these are similar statements, right? Equivalent statements, right? They are equivalent, of course, when the derivatives, both of them exist, right? But choosing this formulation might be more useful for us if the function doesn't happen to be twice differentiable, okay? Very good. So now let me extend these results quickly to the complex case. Oh, sorry, before that, I have to show you the global result, and then I'll extend it to the complex case. Okay? So the second result I want to show you is this. Remember, I assumed before that the Hessian is locally Lipschitz, right? By that I meant that it satisfies a relation like this, close to the minimum for all delta, right? That's what we meant by locally Lipschitz. Close to the minimum, the Hessian changes according to this relation, right? Only in proportion to the size of the step. I want to show actually that because of that, if your function is strongly convex, that local Lipschitz condition actually holds more globally. I want to show that relation 30 holds. What does relation 30 says? Any step you take away from Z0 will satisfy the Lipschitz condition. No matter how far away you move from Z0, the increment in the Hessian will never be more than in proportion to the step you took. It's not just local, it's global. And the kappa prime here is either the kappa that you started with locally, it's the maximum of two quantities, all of them depend on your problem. Delta, upper bound, lower bound, epsilon is the small neighborhood, right? So what I'm trying to say, there exists a kappa prime, which is constant, independent of Z, such that this holds. Fine? So let me show you, okay? We are going to use these results later when we study how well algorithms perform over networks, okay? So that's why I'm mentioning them here, okay? We're not going to go through the proofs again, but you can always revisit them. So let's prove this statement, okay? So what do I want to show? Okay? I want to show that this holds for every Z. Okay? So let's do the following. Let's take that difference. Okay? By the way, ZO is the minimum of the function, right? Just keep that in mind, okay? Now, and let's take this, multiply by any vector x transpose and x from left and right, so you get this, right? Now, the Hessian is upper bounded by delta, lower bounded by nu, right? So the second term here, right, I replace it by something smaller. The first term, I replace it by something bigger, right? So the first line is upper bounded by the second line. Are you following? Okay. And then I group these two terms together, okay? So I'm telling you that, remember, this is a symmetric matrix, right? This matrix here is symmetric, okay, because I'm dealing with real data, so this is probably a typo here. Okay, in this first part, everything is real, okay? So symmetric. So that matrix is symmetric. You see, I have shown that x transpose AX is less than or equal to delta minus nu x transpose x, right? So for any x, so it means that this matrix is less than or equal to this times the identity, right? Okay. So this is one first conclusion, okay, so far. I haven't yet finished my argument, but all I have shown so far is that the norm of this difference is never more than delta minus nu. And remember, delta is larger than nu. Okay, so let's use this property now to establish the lemma. Okay, let's do this. Pick any z inside the small region around z0, right, where the smoothness condition we already know holds by assumption, right? Pick a z inside that region. Okay, then the norm of the difference we already know satisfies that, right? But what was kappa prime? Kappa prime was the maximum of kappa delta minus nu over epsilon. So kappa prime has to be larger than or equal to kappa, right? So this is always true. Fine? Okay. So if z minus z is inside that region, relation 34 always holds. If z is outside that region, then I use this property here that I just proved. Okay? The norm is less than or equal to delta minus nu. So I divide by epsilon and multiply by epsilon. And again, this quantity here, right? This quantity here is upper bounded by kappa prime. And this quantity here is upper bounded by the norm of z minus z0. So either way, you get the same relation, right? And you establish the lemma. You understand? Okay? So these are not difficult properties. Just convince yourself that they make sense, because later we are going to use them. And if you forget where they came from, you can come back and follow the argument. They are not difficult arguments, okay? Fine? Okay, so what I proved here is that if the Hessian matrix is locally Lipschitz, for a strongly convex function, actually it is globally Lipschitz, and we will use this later in our analysis, okay? So this is a useful property, right? I could have given you this as a homo problem, right? Okay, so let's extend these results quickly to the complex case, okay? I don't need to go through all of the arguments because you already know the extensions are not that difficult, okay? So the first statement, remember, we have a mean value theorem, right? We have two versions of the mean value theorem for complex arguments, right? Increments of g and increments of the gradient of g, right? Okay. Just like we did before, you can show again that let's assume, before we continue, that my function is, okay, complex valued now, meaning z is complex valued, and the function is mu strongly convex, okay? Now, if the function is strongly convex when the argument is complex, remember this means that the Hessian matrix is bounded from below by nu over 2, not the nu, right? Remember I mentioned that this 2 will live with us, and this is a difference between real arguments and complex arguments, and I'm going to go around it by introducing a type variable that I'm going to call h. So in the future, I will always write in nu over h, and h will be 1 when your data is real, h will be 2 when your data is complex, so that you don't have to keep remembering this, right? But for now, because I'm doing things separately, I'm separating them, okay? So if your function is strongly convex, it will be nu over 2. So let's assume that it's bounded from above by a similar factor delta over 2, just to be consistent, okay? In the complex case, okay? So if you go back and you use the mean value theorem, the argument is very similar to what we did before, right? You will get that the increment is upper bounded by delta over 2 normal, right? How do you prove this? All you have to do work with the g of v, right? You introduce the vector v, which contains the real part and the imaginary part of z, right? So your function becomes a function of a real argument. And then you apply the lemma that we showed before for this function of real arguments, right? For this function of real arguments, you will have that g at v0 plus delta v minus g at v0 will be upper bounded by the norm of delta v, right? What will go in here, right? And will be lower bounded by the norm of delta v, right? What will go in here? So here should go an upper bound on the Haitian of G, right? What should go here and there, right? These bounds are the ones that will appear here, right? So if you remember last time I showed, okay, last time I showed that if the complex Haitian, I showed you the relation, by the way, between the Haitian in the real domain and the Haitian in the complex domain. Remember that there is a d star relating them, okay? A d star relating them, okay? And because of that, if this is bounded by delta over 2, and remember d star is equal to 2I, the 2 will cancel, so the left-hand side will be bounded by delta I. And from below it will be bounded similarly by nu I, right? So bounds in the complex domain that involve delta over 2, nu over 2, they become bounds involving delta and nu in the real domain, right? Okay? So these bounds here, okay, will be delta and nu. And then you go back to the, right, this is what I'm showing here. So this is the bound. And then you can write down, right? If you go back here, this will be delta over 2, and this will be nu over 2, because this is what we derived in the lemma, right? Remember the integral of t that gives you t squared over 2, right? Integral between 0 and 1, that's how this 1/2 came from, okay? So that's the result here, okay? And again, it means that you can sandwich your function between two quadratics. Okay, very good. Now, the second conclusion that you get from this result, what was it? The second conclusion that I can tell you that G, right, if you remember, I showed you that this, I can write it as this, right, plus I had some weighted norm, remember? Weighted norm with the Haitian at Z0, right? This was in the real case. What is the analog of that in the complex case now? Okay. Now, if you remember, how did I get that result? The result I wrote here on top. Okay. I got that result by integrating, right, an expression that involved the Haitian. Okay. In the complex case, that Haitian is 2m by 2m. Okay. And the mean value theorem, where the Haitian term appears, requires me to extend the delta z's, if you remember. Okay, so if you just repeat the same argument I did before, I'm just calling your attention to why these things come up, right? If you go back to the argument I had before and repeat it in this case, you will get a similar expression. You see, this is a weighted norm of what? Of the extended delta z. That's all. Okay, the extended delta z, because the mean value relation in this case will involve these extended vectors. Are you following? Right, the extended vector delta z, because this Haitian is 2m by 2m, so this will have to be 2m by 1. Exactly the same argument as before, you will arrive at this expression, okay? And the difference will be of the order of the cubic norm of delta z. You could write delta z extended, but the norm of delta z extended is related to the norm of delta z, because they are delta z star, right? Okay? Yes.
In the error term,
yes,
the multiplying matrix with the order of the error term might not be the identity matrix.
Sorry?
The multiplying matrix with the order term, the error term of order of...
What this is saying that error term, its entries, right? By the way, that error term is a scalar, right? It's a scalar because g of z is a scalar. So the error term is a scalar. So the size of that term, right? The size of that term is of the order of the step cubed.
Yes, so my doubt is that when you're doing the integration, you're doing the integration of a matrix term, and then outside you have delta z transpose, and then
yes.
So if the matrix is not identity, it could be some different.
No. We did this argument precisely, right? Let's go back. Here, right? We did this argument exactly here. right? We replace this,
Yes.
okay?
Yeah, but this is the matrix.
Right. This is a matrix, right? So we replaced it by a Hessian plus something of the order of delta Z, right? Okay. Now, I don't really care about the structure of this. It's just some error, right? Whose size is of the norm of delta Z, okay? So this gives you the norm of delta Z under integration. And then delta Z transpose with delta Z gives you the other delta Z squared, right?
So you mean the error matrix, each term of the error matrix is of the order of...
That's what this notation means, yes. That's what this here, that's what this notation means. Each term of the error matrix here is of this order. Is that what you meant?
Yes.
Okay, yeah. Okay. Okay. Okay, I'm moving forward just to get back to where we were, right? So you all understand where this comes from? I don't need to go through the argument. The argument is in your notes, okay? This is a trivial extension of what we did before, okay? Here it is. You have the argument in your notes, right? And that's how you get delta Z, delta Z, delta ZE. Because you see, you can work in the real domain, using 1/2 of the real Hessian, right? And then transform the real Hessian, right? Let's say if you multiply by d star, divide by 1/4, you did not change anything, right? But then use the fact that d times h times d star, that's the complex Hessian, right? So just carry out the arguments. And that delta v times d star is the delta u which contains the delta z. Just carry out the arguments, you arrive at the expression. Okay, so I will let you read that. It's not very, very difficult. And then I repeat the same example I had before. In the quadratic case, what is the Hessian here? Block diagonal C, C transpose, right? Block diagonal C, C transpose. Again, if you perform a completion of squares argument, you can write the minimum value plus z minus the minimizer C, z minus the minimizer, okay? And again, okay, the maximum. So the delta here is lambda max and the nu is lambda min because this is C, not 2C, right? So the Hessian here will be bounded by lambda max of C from above, lambda min of C from below. So you can use these values, right? And remember, we assume that this is bounded by delta over 2, so delta has to be twice that, and the nu has to be twice that. So you just plug these expressions into the lemmas, and you get the bounds for this problem, right? You get these bounds for these problems, which, like I explained before, you could have derived them exactly. You don't need dilemmas for the quadratic case. You just work with the quadratic function, right? And even this expression for evaluating the increment, it's actually an exact expression in the quadratic case, okay? Fine? Okay, so that's what I wanted to cover in this lecture, okay, on Lipschitz conditions, okay? Again, you can continue. Like I said before, okay, if I will just mention these statements because this is similar to what we did before, okay, I don't want to bore you, right? Assuming that the Hessian is upper bounded by delta over 2 is the same thing as saying that the gradient vector is Lipschitz, right? Delta over 2 Lipschitz, okay? Proof, I proved it in the real case. How do you prove it in the complex case? Work with G of V, right? G of V is real. Write down these relations in the real case and then transform them to the complex case, okay? So that's the argument I have, okay, in my notes. You work with G of V, okay? So I'm not going to go through that just because it is not that difficult, okay? You can read it, okay? That's the proof. And then similarly, if you assume that the Hessian is locally Lipschitz, then it turns out to be globally Lipschitz for the same kappa prime defined down here, right? Again, proof. You can apply this to the real version of G of V, right? And then transform it, right? The Hessian in the V domain, we know how it relates to the Hessian in the Z domain. And then you get this relation, okay? That's what I have done in the notes, okay? Fine? So that's what I wanted to discuss with you today, right? Move from the mean value theorems and extract a little bit more information about what I can say in the convex case, right? So I derived a few statements here, which you will see applied often during our analysis of algorithms over networks. Okay, so let's take a short break and we'll continue later.